Here we're going to look at a problem from the 2014 Argentinian Math Olympiad. So let's look at the statement. We want to set capital S equal to the sum of 50 terms given by 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 and so on and so forth all the way up to 1 over 99 times 100. And then next, we want to set capital T equal to 1 over 51 times 100 plus 1 over 52 times 99 plus all the way up to 1 over 100 times 51. So here, one thing to notice is that the second term in each of these products is increasing by 2 and they are all even. So it's going like 2, 4, 6, 8, all the way up to 100. That's going to make 50 total terms. And the first term in these products in the denominators are just one less than the second term. So there we have 1, 3, 5, all the way up to 99. And then next, for the second sum, we notice that we start at 51, go to 52, all the way up to 100 for the first term. So those are skipping by 1. And then the second term is skipping down by 1 from 100, 99, 98, all the way down to 51. So we've got some sort of growth and decline in the two parts of the products for t. Okay, and then our goal is to express S over T in lowest terms. Well, so S is a sum of rational numbers, T is a sum of rational numbers. So obviously, when you take that sum, you're going to get a rational number, which means you can divide a rational number by a rational number and get a new rational number, which has a unique lowest terms. Great, so here are some hints. So maybe the first hint is do not try and find a closed form for S and T. Maybe just if you're interested, you can go ahead and calculate what S and T are like in lowest terms via some sort of calculation program, maybe Wolfram Alpha or Mathematica or something. And what you will see is that they're quite gnarly. So I don't think this is anyway a strategy for getting at this solution. So my second hint will go at, well, what will we do for a solution if this doesn't work? And so I think maybe the best strategy here is to write a more general problem and then use this to form a guess. So in other words, notice this would be like the 50th case of a more general problem because we're adding 50 things in the S thing and 50 things in the term T. And so maybe we could come up with some general problem that looks like adding one thing or adding two things or adding three things, and this is the 50th case of that. But the lucky thing about making this general case is that we can look at special values very, very easily. We can look at the value of the first case or the second case or the third case really, really easily, and that allows us to form a guess about the general case. And then finally, I think the crux of this whole thing, after getting a guess, that might be the hardest part, is finishing off with induction. Okay, so maybe give this problem a go with these hints and we'll come back with a solution. So hopefully those hints were helpful. Now we're ready to attack this problem. Starting with that first hint, which was generalize this problem and use that generalization in order to make a guess for what S over T should be. Then if we've got a guess, it's easier to prove that our guess is correct. So here's what I want to do. I want to consider the following two functions of M. So I want to consider S of M. So this would be like S of 50, just kind of that's where we're getting at. So notice this is going to be 1 over 1 times 2 plus 1 over 3 times 4, all the way up to 1 over 2m minus 1 times 2m. Great. So like I said, if we plug in m equals 50, we get exactly this thing right here. Now it might be useful to write this in like summation notation, and so we can do that by writing the sum n equals 1 to m of 1 over 2n minus 1 times 2n. That's what we'll use for our function S of m. And then for T of m, we'll do something similar. So notice our first thing will look like, well notice here, this is 50 plus 1, so we'll have m plus 1. And then the second term is 100. Well, that's like 2m plus 1 minus 1. And I want to put the plus 1 minus 1 in there just so that it cleans up when we write it down in summation notation. But I'll let you guys think about why exactly we need to do that. So the next one will be 1 over m plus 2, and then 2m plus 1 minus 2. And then, like I said, we're going to go all the way up to 1 over m plus m. So that would be like this term right here. Notice that's just 2m. And then times 2m plus 1 minus m. So we should have the sum as n goes from 1 to m of 1 over m plus n. So there, notice we've got m plus 1, m plus 2, m plus 3, all the way up to m plus m. So that's what we've got there, m plus n. And then here we have 2m plus 1 minus n. So there we're subtracting 1, 2, all the way up to subtracting m. So we've got this new version of t of m. So I just want to point out what our goal is at this point. So our goal is to find s of 50 divided by t of 50. If we plug in 50 into each of these, we get these like things that we started with. So I'm going to go ahead and make a chart. I'll let you guys work out all of the arithmetic in order to see this, but this will give us an idea for how to guess this solution. So I'm going to make a chart where we have these m values, and then we have the appropriate quotient, s of m over t of m. So let's go up to 6. 1, 2, 3, 4, 5, 6. Great. So if you do this calculation, you get 2 for this first one. For the second one, you're going to get 7 over 2. For this third one, you're going to get 5. For this fourth one, 13 over 2. For this fifth one, you're going to get 8. And for the sixth one, you're going to get 19 over 2. Now that might seem a little bit problematic, but if we put everything with a denominator of 2, we'll see a pattern pretty quickly. So notice 2 is the same thing as 4 over 2. 5 is the same thing as 10 over 2. 8 is the same thing as 16 over 2. So look at what's happening at each step. At each step, we are adding 3 to the numerator there. So notice this 4 is equal to 3 times 1 plus 1. This 7 is equal to 3 times 2 plus 1. This 10 is equal to 3 times 3 plus 1, and so on and so forth. So if we go out here, we have a reasonable guess for the arbitrary m term, and that is going to be 3m plus 1 over 2. Great. But now we have a guess up here for our goal, which is exactly equal to 151 over 2. So that's what we'll start the next board off with, a claim that says that exactly. So on the last board, we generalized our problem by defining these two functions, s of m and t of m, and we restated our original goal, s over t, as determining s evaluated at 50 over t evaluated at 50, being the same thing as 151 over 2. So let's go ahead and prove this claim. So we're going to, just for a brief second, look at this like specific case. We will trend back to a more general case and prove that with induction, but we're never going to actually prove this general statement that we ended with. I'll leave it to you guys to fill in the details for that proof of the very general statement. It's not so bad after all of the stuff that we've done. So notice that this is equivalent to, and by this I mean maybe this red star. So red star is equivalent to the following. S of 50 equals 151 over 2 times t of 50. Well, so we just like cross multiplied there. There's nothing really to that. And so notice that that is going to be the same thing as 151 over 2. And now we've got this sum as n goes from 1 to 50 of 1 over n plus 50. And then next we've got 101 minus n. Great. So that's the special case of our t function. Now what we want to do is decompose this thing right here using partial fraction decomposition. So maybe I'll just go ahead and put this in these pink brackets. This is what we'll decompose in partial fractions down here. And maybe what's some motivation for that? Well, writing these two sums as a reciprocal of a product, that really hints that you should be thinking about partial fraction decomposition, given that that's how you solve a similar integral, and integration and summation are really related to each other. Okay, so let's go ahead and do that. So we're going to take this 1 over n plus 50 times 101 minus n, and we will write that as a over n plus 50 plus b over 101 minus n. Now we just have to determine what a and b are. So let's go ahead and take this and clear the denominators. So we will multiply by n plus 50 and then 101 minus n. So let's see what that gives us. On the left-hand side of the equation, we'll have just the number 1. That cancels out. And then that's going to be equal to a times 101 minus n plus b times n plus 50. Great. Now we can extract the constant term from both sides of the equation and then the coefficient of n from both sides of the equation to give us a system of equations that we can use to solve for capital A and capital B. So notice the constant term on the right-hand side is going to be 101a plus 50b. So we get that by distributing this a onto the 101 and this b onto the 50. And then we know the left-hand side of this is 1, so I'm just going to rearrange the order like this. Great. And then we can see that the n term on the right-hand side is minus a plus b, so we have minus a plus b equals, but now notice there's no n term on the left-hand side, so we have this is equal to 0. In other words, we have a equals b. Okay, great. So now we have a equals b, but now plugging that back into the equation which is right above, we see that 151a equals 1. In other words, a equals 151. And that's equal to b by this determination that we had down here. So that means I can go ahead and replace this calculation that I've done here with 1 over 151 here and 1 over 151 here as well. So let's go ahead and clean up maybe this bottom part, and we will insert this here. On the last board, we did some partial fraction decomposition to change this sum, which represents t evaluated at 50. So notice we've still got this 151 over 2 out front, which came from rewriting a different version of this equation up here. But now we have decomposed this into 151 over n plus 50 plus 151 over 101 minus n. Now from here, what I want to do is notice that I can take this 151 and cancel it in both of the fractions, given that I have a multiplier in front of the entire sum and essentially a divider on the inside of the sum. Great, so that means that what we really want to show, and I should say maybe star is equivalent to this statement right now, which is a little bit simpler and looks like s evaluated at 50 equals 1/2 times the sum as n goes from 1 to 50 of 1 over n plus 50 plus the sum as n goes from 1 to 50 of 1 over 101 minus n. And I just broke this up into two parts, given that I've got a sum of two terms, and these are finite sums, so there's no problem with that. And you'll see why we'll do that, because these sums are essentially the same. So notice the very first term of this sum is 1 over 51, then you have 1 over 52, all the way up to 1 over 100. But that's exactly this sum as well. My very first term is 1 over 100, my second term is 1 over 99, and my last term is 1 over 51. They're just going in a reverse order. So I can actually do a nice change of variables that will change this sum into this sum. And that re-indexing will go like this. I'm going to replace n with 51 minus n. So let's see what that does. So that means now I'm going to swap the order of my summation here, but it will still be from 1 to 50. So notice when n is equal to 50, 51 minus n is equal to 1. And then when n is equal to 1, 51 minus n is equal to 50. But now what goes on in here, you can see that this part right here is going to be exchanged with n plus 50. And that's like pretty easy arithmetic to see that. But now we've got two of the same sum. We can just add them together and use that to cancel the half. So in other words, we have our statement is equivalent to saying S50 is equal to this sum as n goes from 1 to 50 of 1 over n plus 50. Great. So this is in fact what we want to show. And we're actually going to make the following claim, which I'll maybe start the next board with, and that is S of m is actually equal to the sum as n goes from 1 to m of 1 over n plus m. We can prove that by induction, but then setting m equals to 50 gives us exactly our solution. Okay, so I'll go clean up the board. I'll keep what we need, and then we'll move on to the next step. On the last board, we worked our goal statement, which was s over t equals 151 over 2, down to the following equivalent statement, that s evaluated at 50. And let's just go ahead and point out that this is equal to our normal s, is equal to the sum as n goes from 1 to 50 of 1 over n plus 50. But we're actually going to prove this by showing a more general statement, and we're actually going to show that S of m is equal to the sum as n goes from 1 to m of 1 over n plus m, and we're going to do this by induction. So let's go ahead and look at our base case. So our base case will be m equals 1. So notice for m equals 1, we have only one term in the sum. So we have 1 over 1 times 2, so that's going to be equal to s of 1. Great. But that's also equal to the sum as n goes from 1 to 1 of 1 over n plus 1. That's again just 1/2. So everything works out for the base case. So now let's go ahead and make an induction hypothesis. In other words, we want to suppose this is true for some m equals k, which is bigger than or equal to 1, and then consider the k plus first case. So we'll consider the k plus first case of the right-hand side and then work it until it looks like the left-hand side. So we'll take this sum as n goes from 1 to k plus 1 of 1 over n plus k plus 1. Great, so notice that is this exactly with m equals k plus 1. And we want to show that this is equal to s of k plus 1. Okay, great. So now I'm going to break this into some parts. So I'm going to first re-index this thing a little bit. So I'm going to replace n with n minus 1. But if I replace n with n minus 1, that means I start at 2 instead of at 1. Notice if n minus 1 is 1, then n is equal to 2. And that's actually going to change this in here also to n plus k. But that's something that we want to do because we're supposing that this statement is true for m equals k. And so we want to leverage that somehow. Okay, so now what we can do is rewrite this as the sum as n goes from 2 up to k of 1 over n plus k. And I want to point out that I left out two terms. I left out the k plus 1 term and the k plus 2 term. And you might say, well, there is no k plus 2 term, but the new upper bound will be k plus 2, given that if n minus 1 equals k plus 1, then n equals k plus 2. So that means we need to add in the k plus 1 and the k plus 2 term. So notice that, the k plus 1 and the k plus 2 term. So if we plug in the k plus 1 term, that's going to be 1 over 2k plus 1 plus 1 over 2k plus 2. So that would be the k plus 2 term. Great. And then one more thing that I want to do is make this start at 1 instead of at 2, because if it starts at 1, then it looks exactly like the right-hand side of this, but we know something about the right-hand side of that. So I'll go ahead and change this to a 1. But I can only change that to a 1 if I subtract off this first term that I really just added on. So I can do that by doing minus 1 over k plus 1. That's the first term. Great. And so now we can use our induction hypothesis on this. So our induction hypothesis is this thing right here. So that's exactly equal to S of K, again, by the induction hypothesis. And now all we have to do is find a common denominator for all of those. So I'll leave it to you guys to find a common denominator and add those rational expressions together. It's not so bad. But what I will say is you get the following setup. So you'll get 1 over 2k plus 1 times 2k plus 2. Great. But now, notice by the definition of SK, if we add in this next term, then we'll get exactly SK plus 1. So in other words, SK plus this next term is equal to SK plus 1. Fantastic. So what that means is that we have proven this general statement right here. But on the previous board, we showed that the 50th case of this statement being true was equivalent to our claim, which solves the problem. So the answer here is 151 over 2. And that's a good place to stop.